That brings us to the normal distribution. The PDF for the normal distribution is this function here. You plug in some value of x, and this function gives you the height of the normal curve at x. These Greek letters are parameters. They're usually given or hypothesized. Mu is the mean, sigma is the standard deviation, and these are population parameters. They are the mean and standard deviation of the population we sample from. The notation we'll use is n mu sigma. When I write x squiggle n mu sigma like this, I'm saying that the random variable x follows a normal distribution with mean mu and standard deviation sigma. The standard normal distribution has mean 0 and standard deviation 1. If we write the function f of x equals 1 over sigma square root 2 pi e to the negative 1/2 x minus mu over sigma squared, with mu equals 0 and sigma equals 1, we get f of x equals 1 over square root 2 pi e to the negative x squared over 2. And if you graph this function, you'll get the purple curve you see on the graph there. If you increase sigma, it widens the curve. This orange curve has a normal distribution with mean 0 and standard deviation 3. It has the same center as the standard normal distribution. They're both centered at 0, but it's wider. And notice that there's more area in the tails. If you draw from the orange distribution instead of the purple one, you're more likely to get a value far from the mean. The green curve has a smaller standard deviation, so it's thinner. Its mean is 2, so it's centered at 2 instead of 0. All of these curves have the same area, 1. They are all probability distributions. To find the probability of drawing a number from a normal distribution, you find the area under the curve determined by the PDF. Before we find areas, let me point out that the normal distribution is symmetric about its mean. For a normal distribution, the mean equals the median equals the mode. What this means in practical terms is that when we're looking for the area that's a certain distance from the mean on both sides, we can find one side and double it. For example, let's say mu equals 0 here. The area to the right of x is the same as the area to the left of negative x. You'll see why this is useful soon. Every normal curve runs from negative infinity to infinity. The area under the curve is always 1. If I want to find the probability that a number drawn from a normal distribution is less than or equal to little x, I find the area of the curve that's behind little x. For those of you who have taken calculus, that means I have to integrate the PDF from negative infinity to little x. I have to solve this integral from negative infinity to x over sigma square root 2 pi e. I'll make this a t. dt. Even if you know calculus, this is not easy. There's no closed form solution for this. The only way to solve it is to use a numerical technique like Simpson's rule or the trapezoid rule. Even if you understand the math, it's a lot of work. So we let the computer do it. In R, the area behind x for a normal curve is given by the pnorm command. The area ahead of x can be found using 1 minus pnorm. You can also set lower tail equals false in the pnorm command. They give the same result, but sometimes this one is more accurate for really small areas. Like if this one gives 6 to the negative 85th, this one might give 0 because 6 to the negative 85 is so small, but it doesn't really matter in practice which one you use. Here's an example. If x follows a normal distribution with mean mu equals 2 and standard deviation sigma equals 1/2, what is the probability that x is less than or equal to 3/2? We can get that from R using p norm 1.5 to 0.5, and the answer is 0.1587. What is the probability that a random variable drawn from the same distribution is greater than 3/2? Now we want the area in front of 3/2. Because the area under the curve is 1, the area ahead is 1 minus the area behind. 1 minus 0.1587 equals 0.8413. There is a 84.13% probability of drawing a number greater than 3/2 from this distribution. Now I'm doing the same thing with the normal distribution where the mean is 0 and the standard deviation is 3. The probability that x is less than or equal to 1 is 0.63 using the p-norm command from before. The probability that x is greater than 1 is 0.37 using the same process as before. Now, what if I want the probability that x is between -1 and 1? How would I find this area? There are a few ways to do it, but probably the most straightforward is to find the area that's less than 1. So the area less than 1 would be like this. And then subtract the area that's less than -1. So if -1's over here, we'll subtract this area, and what's left is this area here. To get that from R, you would enter p norm 103 minus p norm -103. Another useful command from R is qnorm. I think that means quantile norm. A quantile is the same as a percentile, but it's written as a proportion rather than a percent. But this will give you the quantile of the normal distribution you specify. For example, if we have a normal distribution with mean 25 and standard deviation 3, what is the 0.75 quantile? What is the number such that 0.75 or 75% of the area is less than or equal to it? You plug that into R's qnorm function and it returns 27.02. For this distribution, there is a 75% probability that you'll draw a random number less than or equal to 27.02. I'll show you how this works. Our last example had an N25-3 distribution, and 75% of the data was less than 27.02. So P norm 27.02 25.3 equals 0.75. I can standardize this by subtracting mu, which is 25, and dividing by sigma, which is 3, and this new random variable will follow a standard normal distribution. 27.02 minus 25 divided by 3 is 0.673. If I put p norm 0.67301 into R, it should give me 0.75. If I look on this table here, when Z begins with 0.6 and the second decimal place is 0.7, the probability it gives me is 0.7486. And you can see from this table that 0.75 would be somewhere between 0.67 and 0.68. In olden times, before everyone had computers and calculators that could do statistics, they had to standardize their normal distributions and look them up on tables like this. Because, like I said, the calculus required to find these areas is too tedious to do by hand. A well-known fact about the normal distribution is the 68, 95, 99.7 rule, which says that if you sample from a normal distribution, about 68% of the values will be within one standard deviation of the mean. About 95% will be within two standard deviations, and 99.7% will be within three standard deviations. So, as we've seen, with the normal distribution, you're most likely to get something near the mean, because that's the mode, that's where most of the area under the curve is. You very rarely get something more than three standard deviations away.